Hello and welcome to today's module. So, we are going to discuss high level specification of an analog front end targeted towards biopotential recording, and the target biopotential in this example is going to be neural potential. We are going to look at a front end design which is supposed to acquire neural potential from a non-invasive electrode. So, that electrode is basically supposed to be in touch or in contact with the skin on the skull, and it is supposed to acquire very minute biopotentials coming from that electrode. So, we are going to look into the design specification of that front end, what are the fundamental building blocks in that particular front end, and try to determine the specification of those blocks based on the characteristics of the electrode and the signal that we are acquiring. So, we will see how first of all the signal definition, signal characteristics and the electrode characteristics play a role in determining the characteristics of the overall front end. We will break down the functionality of the front end into the constituent blocks, namely the front end amplifiers, filters, analog to digital converters, the other blocks which are supposed to address some of the signal non-idealities in form of filters, offset cancellation blocks and so on. And then from there we will try to arrive at the specification of each of those individual building blocks. Once we have done that, we will go down into each of those units, each of those fundamental building blocks, and try to look at the basic analysis, circuit level analysis required to implement those blocks. That analysis may include some of the very fundamental design steps like DC biasing, DC analysis, frequency response, noise analysis, signal swing analysis, stability analysis and so on. So, these are the fundamental steps which will be required to arrive at the final design. Once we have done that, next we will be looking at the transistor level design and trying to figure out the right sizing of the transistors, with the help of which we can meet the specifications for some of the crucial parameters like bandwidth, gain, noise, linearity and so on. So, we will follow this same strategy for all the blocks. So, starting from the highest level, going to the block level specification for each of the block, looking at the fundamental circuit analysis to determine the specs, and then looking at the transistor level designs to meet those specs. So, that is going to be a strategy for all these blocks involved in the design. And beyond that, we will be looking at topology level differences also. Not only circuit design for a given topology, but we will be looking at variations of topology, that if it is a front end amplifier, what kind of a front end amplifier can be suitable. If we are looking at different variants, what are the pros and cons with respect to the design steps or with respect to the specifications. Likewise, if you are looking at filters or A to D converters, if we go for different choices, if we choose different topologies, what are the pros and cons, which topology gives us advantage in what scenario. So, we will having discussion at topology level also. So, apart from the bottommost design steps and threadbare discussion on transistor level design, sizing, etc., we also have discussions at all the steps, even at the highest level where you have to figure out right topologies and select the right kind of building blocks for your system. So, let us get started with the definition of the signal. Let us first see what is the signal characteristics, the electrode characteristics through which we are acquiring the signal, and based on which we will be determining the specification of the front end amplifier. So, if you look at the neural potentials, acquisition of neural potentials in general may require use of two parallel electrodes. So, you may have two parallel electrodes from which the data is being acquired, and it is fed to our analog front end sitting on a device which is having a differential amplifier at the very first stage. So, the detailed mechanism for the neural potential creation, how does the potential difference arises between two contact points on the electrode, that is going to involve detailed discussion about the biophysics, which we are not going to do in this particular module. For the time being, the assumption is that between two contact points, between two electrodes, there is going to be a electrostatic potential created because of the neural activity in this region, and this potential is being acquired by a electronic device, an integrated electronic device, the very first stage of which is going to be a differential amplifier, which is going to process the difference between the electrical signal acquired from these two electrodes. Now, we next need to look into the model of this electrode. What are the features or electrical characteristics of these electrodes? In general, these electrodes can be modeled as a parallel combination of resistors and capacitor. For a standard dielectrode that has been popularly used in literature, the R values will be in the order of mega ohm. It can be all the way 1 to tens of mega ohms, and the capacitor values can be in the range of nanofarad. So, here is your biopotential that you are trying to acquire. So, you can assume that this is your V in that you are trying to acquire, and right at the interface of the electrode and the skin there can be a time varying potential because of the defects at the interface or because of the artifacts at the interface. So, that also in general is modeled as a time varying signal. We can call it V offset, which is the property of the electrode and skin interface. This is not a desired signal, but it can be much larger in magnitude and it can overwhelm your desired signal. So, this kind of signals are always dominantly present whenever you are looking at contacts of electrodes with the skin. So, because of the interface defects or because of the artifacts between the electrode and skin contact, there can be an offset voltage created, which is very slowly varying signal, but it can be very large in magnitude. We will look at the specification of this as well. So, this is the input signal which is going into our differential amplifier. Likewise, you have another channel which is also having the similar electrode model, only thing is it will be having a V into the negative terminal. Now, here if we look at the electrode characteristics, the R of the electrode is almost acting like a source resistance, and this is pretty large, it can be 10 mega ohm. As a result, if we want this minute signal to be amplified nicely, we would like to have the input impedance of our amplifier also to be pretty large, maybe larger than 10 mega ohms to few hundreds of mega ohms, so on. So, we want this amplifier, the very first stage of the amplifier, to have very high input impedance of the order of say few tens of mega ohm. So, looking at the electrode, I can say that the R in of the amplifier should be 10 mega ohm or higher. So, this is the first specification we can arrive at just by looking at the electrode characteristics. Now, if we look at the signal, we have to first of all find out the characteristics of the signal, frequency domain and time domain characteristics of the signal. So, the biopotentials recorded through these electrodes may have an amplitude ranging from 10 microvolt to 100 microvolt, and frequency content may range from 0.5 hertz to 100 hertz. So, that basically gives us the specifications for the overall signal gain and bandwidth of our front end stage. So, at least looking at this signal, the highest level specification that I can arrive at will be bandwidth, say being a little bit more conservative, 0.1 hertz all the way to say 100 hertz, and the input signal range or dynamic range which the amplifier should be able to handle should correspond to this input range 10 micro to 100 microvolt. Along with that, we also need to verify what is the gain requirement for the very first stage. So, if the input signal minimum value is around 10 microvolt, what is the gain required by the amplifier? So, we need to look at the gain. Also, we need to look at the noise, the equivalent noise of this amplifier. So, during the basic noise analysis, we have seen that the total contribution of the transistors, the total noise contribution of the transistors in a particular circuit can be modeled as an equivalent input referred noise. Ultimately, the signal of the circuit will be available at the output. So, we will be looking at the signal available at the output of the amplifier, and therefore, if the transistors in this amplifier are producing noise currents, noise voltages, their effect will be definitely visible at the output. So, how do we define the input referred noise? The total noise signal produced at the output in absence of any input signal divided by the gain of the amplifier can be seen as the input referred noise. So, when you do not have any signal applied to the amplifier, the transistors, resistors inside the circuit themselves are going to produce noise signals, noise voltages, and and because of which the output node over here will have minute fluctuations corresponding to the noise voltages. So, if I want to say what is the equivalent input noise which would produce the same output noise if it was an ideal amplifier. So, that will be obtained by dividing the output noise by the gain of the amplifier. So, that is a simple concept of input referred noise that we have discussed during the noise analysis. We will be revisiting that concept and looking at it with respect to our differential amplifier and operational amplifier circuits that we are going to build. So, we are here we also need to specify what is going to be the noise requirement, what should be the limit on the input referred noise of this amplifier, so that it does not corrupt the desired signal. So, determining noise is relatively straightforward if we know what is the precision with which we want to record the input data. For example, if the input level can go down all the way to 10 microvolt, I would need to ask how much signal to noise ratio I can tolerate. So, signal level is 10 microvolt. If I have RMS value of the noise close to 0.1 microvolt, that means the signal to noise ratio is around 100, and that means I have at least 1% precision. The noise level is lower than 1% as compared to the input signal range. That would also in effect determine with what precision I can record and digitize the data. For example, if your noise level is more than 1% of the data, effectively the maximum resolution that you can have for the digitized data is also going to be limited to that 1%. So, 1% means you have at the max 7 to the power of close to the power of 7 different levels or 100 different levels. That means you can have at the max 7 bit precision for the data recording. So, that would mean that if I want a 7 bit precision or if I want 100 different levels in the recorded data in the digitized form, I would like to limit my input referred noise below 0.1 microvolt, and that necessity, that need once again has to come from the end user. So, the people doing the digital signal processing on your processed analog data, they have to tell you that how many bit precision are required, so that they can do the accurate digital signal processing and find out or extract the required information from that data. So, that will give us the specification of the noise. So, let us say that we are happy with around 7 bit of precision, and as a result we will be looking at an input referred noise or targeting an input referred noise that is within 0.1 microvolt. So, we have looked into 3 critical parameters, the R in, the bandwidth and the noise. Now, the fourth one that we have left blank was the gain. Now, in order to look at this gain, we need to look at the unwanted signals also, which is coming along with our desired signal V in 1, and we need to look at what is the amplitude and the frequency content of this undesired V offset signal. This is an undesired signal which comes because of the artifact at the interface between the electrode and the skin. So, the V offset may have an amplitude all the way up to few hundreds of millivolt peak to peak. That means, it is much stronger than the desired signal V in 1, and the frequency content of the V offset may be is going to be less than say 0.1 hertz. So, in general this offset is going to have a very low frequency variation. So, it is a very slowly changing signal. We call this generally dynamic offset. So, we have studied earlier the concept of offset in the circuits. They are static offset because they are constant over time. So, if you have mismatch in the differential amplifier, we get an offset, effective offset in the differential amplifier, but that is constant over time, therefore, we term them static offset, whereas here we have an undesired offset coming from the electrode, an undesired very large peak to peak, but slowly varying dynamic offset coming from the electrode, and we term is dynamic because it is changing with time. So, basically both the terminals positive as well as negative will have such dynamic offset. So, we need to look at the difference, how the difference between these two dynamic offset is changing, and that is basically the input dynamic offset to our amplifier. And we see that its value is pretty large, it is 100 millivolt peak to peak. And now, the question is that if we have to cater to this 100 millivolt peak to peak signal, considering the supply voltage limitation of our circuits, we must make sure that after amplification this 100 millivolt signal does not lead to clipping, because if we assume that this entire 100 millivolt signal is passing through our amplifier, that would mean that after the amplifier the small tiny desired signal sitting on our dynamic offset signal is going to ride onto this even after the amplification. So, at the input point we have this large dynamic offset V offset, which is very slowly varying signal. On the top of that we have this high frequency signal, which is our desired signal V in 1 sitting on it. Now, if we look at the supply voltage, suppose for 180 nanometer CMOS technology we are targeting low power design, and for that we have chosen the supply voltage around 1 volt. In general, for 180 nanometer technologies you can have a supply voltage up to 2 volts, but for low power design we can go for 1 volt. So, assume that the supply voltage chosen for this front end design is around 1 volt, and in that case the maximum swing at the output of the amplifier can be 1 volt. So, if you are designing the amplifier with peak to peak output swing, maximizing the swing, in that case suppose you can approach 1 volt. So, in that case if I have to accommodate this entire 100 millivolt peak to peak signal, I cannot afford to have more than 10 gain, because after that this signal will start getting clipped. So, if this starts getting clipped, then of course this tiny signal sitting on the top of it will also be destroyed. So, we do not want this large peak to peak signal to be clipped, provided it is able to pass through the front end amplifier. So, that means the maximum gain that you can have for the amplifier will be just 10, and even after amplification the desired signal, it is getting amplified only by a factor of 10. So, from 10 microvolt it will be able to get to 100 microvolt, which is again not at all enough for further processing. And then one of the crudest way that you can handle this problem is that after this amplification you can try to apply a strong high pass filter, so that it suppresses this slowly varying signal, and then you amplify the rest of the signal, which is the desired signal. So, that is one possible way that we can think at the highest level, that you amplify both the signal little bit, and after that you apply a filter which is going to be very sharp cutoff frequency filter, and as a result you reject the slowly varying signal and then pass on the remaining desired signal, and in subsequent stages you can keep on filtering further. But in general that is not a very standard way of doing it, and that may not be a very efficient way of doing it. We will see later as we progress along the design, we will see that there can be some ways in which you can incorporate a high pass filtering operation in the very first stage, so that this slowly varying signal can be cancelled out in the very first stage to a good extent. As a result, basically what we are trying to say, that the first stage is doing the job of an amplifier as well as a filter, which is allowing me to reject the undesired slowly varying signal to a good extent, so that at the output I am able to suppress this slowly varying signal. So, its peak to peak amplitude does not increase as much as compared to the desired signal. So, desired signal gets amplified significantly, but the slowly varying dynamic offset does not get amplified that much. So, what we are trying to say is that the ratio of peak to peak amplitude of the desired signal versus undesired signal should be enhanced. So, we cannot claim that the magnitude of the desired signal will definitely be larger as compared to the undesired signal. That is not necessarily the criteria. If that happens, that is the best case, but at least we should be able to significantly enhance the ratio of the amplitude of the desired signal over the undesired signal. So, after passing through my first stage amplifier itself, I would like that the undesired slowly varying signal is significantly suppressed, whereas the desired signal riding on the top of this is magnified or amplified. If this happens, and if we say that the undesired signal has been suppressed significantly and I am left with only the desired signal, in that case what is the maximum gain that we can have here? So, the maximum peak to peak signal over here, it can go say all the way to 1 volt, and you are having the input signal which is around 10 microvolt. or in that case we can say that the overall gain that you can have is going to be 10 to the power of 5. But once again we are going to keep some room, because completely eliminating this strong slowly varying signal will not be feasible. There will be a remnant portion of it which can be comparable to the input signal or even larger than the input signal. It may happen that you still have a significant portion of the slowly varying signal, on the top of that you have your desired signal. Therefore, we would like to keep some room or some margin for the undesired signal, and we will see that why it is important. Using pen and paper we can try to come up with a design which is able to completely suppress this undesired signal also. That is feasible, at least in simulations, on paper, on calculation it is possible to completely suppress this as compared to the desired signal. But there can be changes over time in the transistor components or the resistor components, or because of process variation you may not get the exact characteristics. Therefore, you want to have some margin, so that even if the undesired signal is not completely eliminated, even if it is still having sufficient component and it is stronger than the desired signal, I have certain room. For that I will keep an assumption that my desired signal is magnified at the max, say to 100 millivolt before it goes to the ADC. So, before the signal reaches the ADC it has to be amplified to the maximum extent, so that the ADC can get the maximum amplified process signal. So, before the signal reaches to the ADC I am assuming that my desired signal is amplified all the way to 100 millivolt. So, from 10 microvolt it is going to around 100 millivolt. In that case the maximum gain that you are having is 10 to the power of 4 combined together, all the stages combined together reaching up to the ADC, we are expecting that the total gain is going to be 10 to the power of 4. So, in that case what we are assuming is this weak 10 microvolt signal will be able to get to around 100 millivolt before reaching the ADC, and in that case even if we assume that this signal has not been suppressed, the undesired signal has not been suppressed, it will still comparable to it or even larger than that, still we have enough room. Even if the desired signal is having 100 millivolt peak to peak and the undesired signal even if goes as bad as 1 volt peak to peak, still the signal may not be badly corrupted, still the clipping will not occur. That is why we are keeping this margin, we are allowing room for this undesired signal, so that in worst case if its amplitude is not suppressed, it is still not leading to clipping of the desired signal. So, we are limiting the peak to peak signal that we want for the desired signal before we reach the ADC. So, that gives us the requirement for the overall gain. This may not be the gain of the first amplifier stage itself, but remember there are going to be other stages also, there are going to be filters, and the amplifier itself may have multiple stages, as we will see. So, the overall gain combined together before reaching the ADC, we are assuming that this is the total gain of the system. Now, we also need to look at some other important characteristics, like say the power budget, what should be the overall power dissipation of the front end system, and that again is dictated by an application. So, if you are envisioning an application where you have a multi-channel interface, you have several tens of these electrodes coming onto your integrated device, you would like to minimize the power dissipation in each of these channels, and the power dissipation again has conflicts with many other parameters, most importantly noise. So, the user can give you a ballpark number that to start with you have to have total power dissipation within 1 milliwatt, and if you are having say 10 such channels coming in, each channel should have a budget of 100 microwatt. So, we start with an assumption that the power budget given to us is 100 microwatt per channel. So, that the total power dissipation combined for all the stages is limited within 100 microwatt, and we will see that what is the division of this 100 microwatt, as there are multiple stages in this front end. We will see that majority of that power dissipation can be taken up by the front end amplifier, because there we have the serious noise constraints, because this must be low noise, and as we will see during the noise analysis of our transistor level circuits, the low noise criteria translates to requirement of sufficiently high bias current, and as a result this is going to be our most power hungry block. Beyond that, there are of course other units like the filters and the ADC, which can also consume significant fraction of the power. So, this entire power budget needs to be judiciously divided among those multiple stages. Apart from that, of course, we have the input range. What is the signal range? So, that is now obvious, because the input range must cater to the entire signal. It must be able to accommodate the desired as well as undesired signal, because at the input point we do not have any cancellation whatsoever. We are assuming that this amplifier is at least having some high pass function, so that it is able to suppress the undesired signal and therefore pass only the high frequency desired signal, but before that we do not have any such filtering. So, at this point you definitely have a very strong undesired signal having several hundreds millivolts of peak to peak magnitude. On the top of that you have this weak signal sitting, and therefore, the input range, input signal handling capacity of this amplifier must be able to accommodate this entire range. So, well known range of this input offset can be few hundreds of millivolt, and therefore, we would like our amplifier to have as large input range as possible. So, we would like to design the amplifier such that it is able to accommodate maximum possible range. So, let us call it a rail to rail input swing. So, ideally we would like to have rail to rail input swing. That means, it should be able to handle signals within 0 to VDD. Even for input signal going all the way to VDD, the amplifier should be able to operate, or going down all the way to 0, it should be able to operate. So, this is the ideal case, but in order to accommodate few hundreds of millivolts of signal, we should be able to ensure that we are as close as possible to the maximum possible rail to rail swing that we want to have. So, let us go with the best case possible, and then we will figure out that for a particular topology what kind of input range can be obtained. If we choose a particular configuration of the front end amplifier, some configuration can give us more a larger swing, or it can be closer to rail swing. Some other topologies may be better for some other parameters, but they can limit the input swing. So, there the topology level choice also comes into picture. What topologies to choose for the particular amplifier, so that we are meeting the input range criteria as well. So, here we have determined the high level specification for the very first stage, and we have assumed certain things. We have assumed that the first stage amplifier is also having a high pass filter functionality inbuilt into that stage, and we are assuming that this is going to be broken down into multiple stages. So, this is not necessarily a single amplifier, it may have multiple constituents, but what we are assuming is the overall gain has been captured here, and we are modeling the overall gain as A, and which is close to say 10 to the power of 4. After that, before we go to the analog to digital converter, we need an anti-aliasing filter, which is can be a low pass filter. So, just to band limit the signal and avoid aliasing, we know that we need to limit the signal frequency content, and for that we need a low pass filter before we go to ADC. So, here if we look at the signal content, we are assuming that the signal is band limited within 100 hertz, and therefore, the low pass filter cutoff frequency can be close to 100 hertz. And once again we have to see whether in order to meet this 100 hertz frequency, we can choose the standard op amp based circuits with RC feedback, or we need to go for other topologies which can meet such low cutoff frequencies without taking a lot of area or a lot of power on the integrated circuit design. So, we will look at a couple of topologies which are good alternatives to very bulky or area consuming op amp based filters, which can facilitate filter design with very low cutoff frequencies without the need of very bulky passive component RNC values. And then finally, we have to look at the ADC, and this can also have several specifications in terms of resolution, sampling frequency. Bit precision comes from the end user, as we have discussed. The people doing the signal processing on the digital side may tell you that this much bit precision is required, and that has in fact translated to one of our input specification, that is the input referred noise. Likewise, there can be other specifications related to linearity that we also need to consider over here. Linearity and distortion plays an important role in determining the specifications of the ADC, and we will visit those also. But two very fundamental specifications are resolution and sampling frequency. So, sampling frequency once again depends upon the signal bandwidth, and here since we are saying that the maximum frequency content of a signal is going to be within say 100 hertz. So, our sampling frequency required for the ADC may be at the max few hundreds of hertz or say a kilohertz. We will see that there are certain ADC topologies where intentionally you can try to keep higher sampling frequency. They are called oversampling data converters, which can have some advantage in terms of signal to noise ratio. So, probably we will have a high level discussion on those kind of topologies also, where you intentionally keep the sampling frequency high. So, we will go deeper into each of these blocks one by one and look at the basic design steps involved in the constituent circuit components for each of these blocks in the subsequent sessions.